yesterday we were speaking about the Armizo condition plus this additional curvature condition here, which is called the which combined with this Armizo is called Wolff condition. Now the question is that it is very important that we have a much better geometric understanding of this Wolff condition, and how does it avoid this short step length. And once it is done, we will show that in fact the Wolff condition can there could be an alpha, we can show the existence of an alpha which will satisfy the Wolff condition. Now it is important to understand this function phi alpha once again. So let us look at this function phi alpha which we introduced in the last lecture for a given k. Of course this phi alpha you can say phi k alpha also, does not matter, but okay, let us just give phi alpha for the time being. We know that we are analyzing things at the kth iteration, and this is the descent direction. Now what happens if I put alpha equal to 0? If I put alpha equal to 0, it will become fxk. Now you know that f of xk is not the minimizer. Now which means in the neighborhood, around the neighborhood of that point xk, there is a point where the function value is better, means it is lesser. In the sense along the direction dk the function value is actually decreasing. So for certain alpha between 0 to alpha naught, which since dk is a descent direction, for all alpha element of some alpha naught, I know that f of x k plus alpha dk is strictly less than f of x k. So this would allow us to draw the function better, in the sense that you see that here so if this is my f of x k, so this is alpha and this is my phi alpha. So up to certain threshold alpha naught here, my function value is decreasing, is less than this f of x k. Then of course after that it can increase and then it can decrease and whatever. So this is my phi alpha, but the threshold alpha naught, till this threshold alpha naught it decreases. Now my line L alpha, so here what does it mean? It shows that phi of alpha is less than equal to phi of 0 for all, or rather strictly less than phi of 0 for all alpha belonging to between 0 and alpha naught. Could be equal to alpha naught, but okay. So phi alpha is a continuous function because this f is continuous, because of function f is differentiable. Now this line L alpha goes like this and cuts up. So what happens is, you might question, okay, whether L alpha is below this. Okay, L alpha could be like this also. It depends on the type of slope you take. If you take a moderate slope here, the line L alpha, which you know is nothing but f of x k plus C1 times alpha into grad f x k into dk, inner product dk. So if you take a proper slope, a proper modulation of C1, then you know for a large chunk the L alpha line lies above this graph, and that is a crucial fact. So you can say, okay, this is my acceptable alpha naught, this is my acceptable alphas. Now what the curvature condition does is the following. If you look at phi alpha, Curvature condition is the second condition. So, curvature condition plus Ormizzo condition gives you the Wolff condition. So, if you look at phi alpha here, so this phi alpha is this function again f of x k plus alpha dk. So, now let us do one thing, I take a derivative of this because it is a function. This derivative, if you compute out very carefully, is by applying chain rule. So, first the gradient of this into the derivative of this, which is nothing but dk. So, it is slope of the function phi dash at any alpha say this alpha, this is an alpha. So, this is nothing but phi dash alpha, the slope of this function, slope of this line is phi dash alpha, right. Now, what happens is that if you look at phi dash 0, if you look at phi dash 0, then phi dash 0 is nothing but grad of f x k dk. So, now basically then because C1 is less than 1, this is bigger than C1 times say alpha times, there is some alpha, sorry I would rather say this C1 into. So, the slope of this, now the slope of L dash, what is the slope of L dash alpha, what is that, what is L dash alpha? L dash alpha is nothing but C1 into grad f x k dk, it does not matter what is the alpha. So, L dash 0 is also this, L dash 0 is also nothing but for the same thing. So, what I am expecting is that the slope of this line must be bigger. So, phi dash 0 is bigger than L dash 0, L dash alpha, this slope, which is natural because C1 is, so C1 is between 0 and 1. So, this whole thing is nothing but a fraction of this. So, this one is bigger than this one. Now, you can say okay, these are all negative, bigger than this one in this sense, sorry I make a mistake, fraction of this one. So, because sorry I made a mistake, this is negative, this is negative. So, now you take a fraction, so fraction of the whole thing. So, it is minus 1, you take minus half. So, minus half would become bigger than minus 1. So, this slope has to be smaller. So, this slope has to be smaller means what? I made a mistake here, it had to be less than equal to, those who had recorded greater than equal to, please change it. This is not positive, this is negative, this decay is a descent direction. So, this slope has to be smaller means what? That the angle, so this is less negative and this is more negative. More negative means what? So, this is an obtuse angle, this is the slope, okay, which is the negative slope, and I should have some another slope. I should have a line whose slope is like this. Let me consider a line whose slope is like this. So, slope of the function at 0. So, slope of the function at 0 is this, which is less than C1 times this. So, when the obtuse angle is more, the tangent would be lesser and so here a tangent. So here this slope, this one, that is for slope at phi dash 0, can be viewed as a slope of a line. We can basically draw a tangent to the curve of phi dash 0, and wherever this is cutting the line, cutting the x axis, that point, till that point I won't accept any alpha. So beyond this, for all alphas, this whatever slope you are taking, all of the slopes would satisfy this condition. See, some slopes would be, for example, okay, here this is up to alpha naught, right. So here you know the slopes are all coming down. So this particular slope has to be, for all this, from starting point from here, the slope, this slope is always less than this slope, which means that find an alpha. So corresponding to this alpha on the curve, I start accepting my alpha, so I am not very near to the starting point 0. So this is the whole idea, that you have another curve whose slope is another, you basically draw a tangent to this curve at the point alpha equal to 0, tangent to the curve phi alpha, and then you see that where that curve or where that tangent cuts the x axis, from there you consider, from right to that till alpha naught you consider your acceptable alpha. So this is your acceptable alpha now, this part is your acceptable alpha. So this is basically the idea of the Wolff condition, and now we will write down a very fundamental result which says that the Wolff condition actually gets satisfied. The Wolff condition gets satisfied for very simple scenario. So let us write down the result and then we will prove it on the blackboard. So let f be a function from Rn to R is continuously differentiable, which means smooth. So it is continuously differentiable let dk be the direction of descent at xk. xk, and assume that f is bounded below on the ray. So it becomes a one dimensional minimization problem. You see, f is bounded below on the ray, that it has to be this. Then if we have this constants, fix some constant, there exists, then if this happens, there exists intervals of step length satisfying the Wolff condition. So this is something you need to really remember. It's not that you need to be very bothered about it, but it's good to have an idea of the proof so that you get into the habit of knowing that even in this issues of numerical optimization, we have to be really careful of taking care of the mathematics. Whatever statement we make, we need to prove it, even if we are making these sort of approximations with Wolf conditions etc. and Armizo condition trying to find alpha approximately. It is imperative on us that our alpha, that whatever we want, such an alpha exists. So, when we run the algorithm, we are sure that if we are doing such an operation, this operation would actually give me something. Okay, so now we will go for the proof. Now you see what happens is that just after alpha equal to 0, that is x equal to xk, the function value decreases quite sharply, because that is what would happen till an interval alpha naught, and then it starts increasing a bit and goes up. And you know this line L alpha, this is unbounded below, because if you take the line L alpha, there is fxk plus c1 times alpha into grad fxk dk. Now grad fxk dk is negative, c1 is positive, alpha is positive. So I can now, if this is negative, I can make this alpha going towards infinity and make the whole thing negative and larger in the negative sense. So this value will keep on dropping, keep on dropping, keep on dropping, but it will not have a bound. Now f is assumed to have a bound. So basically now this line L alpha at the very beginning, because what would happen is I can always have an alpha. So for till alpha naught, so here, so till alpha naught the function values are decreasing. So f of x k plus alpha dk is strictly minus fx naught, fx k is strictly less than 0. So these are fixed for a given alpha. So if alpha is between 0 and alpha naught, by looking at this diagram, then this difference is strictly less than 0. So it is some number, some k. Now I can multiply this grad fx by this alpha part and multiply by a chosen c1 between 0 and 1, so that I can make this. So this number, this alpha k, can be made to be less than c1 into, we can choose c1 like this, right. We can always choose c1 like this, because this is approximately this value, because by Taylor's theorem, what would happen is, by Taylor's theorem you can write this as nothing but, or by the very basic definition of differentiability, you can write this as small o of alpha. So now this thing, so which means that this thing is strictly less than 0, this whole thing, this thing is strictly less than 0. Now I know that this is also strictly less than 0. Now what I can do for alpha very small, I can now, if I divide by alpha, I will have f of xk plus alpha dk minus f of xk divided by alpha is equal to grad of fxk dk plus O alpha by alpha. Now this is true for any alpha. If I make the alpha very small, I can make this thing very small, and this will be, this negative part will overrun this even if it is positive. So this will basically become negative. Now what I can do, this is, of course, I can make the whole thing to be less than some C1 between 0 and 1. This is of course true. So this whole thing is negative, this is less than a fraction of this. So fraction of this is bigger than, I can take a C1 in such a way that this whole thing is less than a fraction of this, because this will become very small. So this will dominate, and hence this can be made to be less than a fraction of this, which would be bigger in the negative sense, which will be more near 0. So then what happens is that, so for alpha, for all alpha between 0 and alpha naught at least, right, I can have f of xk plus alpha dk less than equal to f of xk plus c1 into alpha times grad fxk dk. So I meet the Armizo condition. Now you see, I have said that up to alpha naught, till alpha naught, this point, my Armizo conditions are met. So maybe I take some alpha here, right, or some alpha just slightly less than alpha naught. Now in this interval, this is a continuous function in this and in this interval it will have a minimum, okay, possibly the minimum is here and then it is going up like this. Now what happens, because this is unbounded, this line, there will be a first point where it first intersects this curve. So now I can find a band of alpha, right. So here it will intersect this curve. So if you observe from the geometrical picture that all the curve now is lying below this line. So from this alpha star where it intersects, I will have the sufficient decrease condition holding. So that is, so if alpha dash or alpha star, if alpha star is the first point or is the first point of intersection then for all alpha between alpha and alpha star, basically, so for all these function values are less than f of xk. So here was my f of xk value. Here what would happen is that in this particular picture, starting from alpha dash, all the function values are basically less than f xk. F xk is here. All the function values are less than f xk. So you know that what happens is this thing comes down after f xk in a neighborhood and then it starts rising up. The function value comes down, which takes the minimum value in this certain interval, and then it starts rising up where it comes and hits this curve, that is it becomes equal. So then at that point what we would have is that f of xk plus alpha double dash alpha star dk is f of xk plus alpha c1 and alpha star f of xk into dk. So this is what will happen. So you see, we have found the Armizo condition. So this alpha star at which it intersects, for all alpha star which is less, for all alpha element of alpha star, for alpha star we would have this. So for all alpha element less than alpha star we would basically have this. That is what you can see from the diagram. Now the next point is that we shall use the mean value theorem. So let us do that here in this thing, is that now you have got this alpha star, so let us use f of the mean value theorem. Alpha star times dk minus f of xk this is equal to alpha start times grad of f of x k plus some alpha double dash dk, where this thing is lying between this point and this point, is a point inside lying in the interior of the line segment joining these 2 points. Now what we have? We also have this expression, that was from there, because at this point alpha star, it comes and intersects the line comes and intersects the curve. So here what you can do is this. Now look at this difference. So what I am having is the following. I am having, so this would imply that grad of f of x k plus alpha star dk, alpha double dash dk dk is equal to this one C1 times, now C2 is, this is a negative quantity, now C2 is lesser than C1, right. Now C2 is lying between, bigger than C1, C2 is lying between C1 and 1. So naturally this would be, if since C1 is lesser, then this would be less negative than this one. So C1 is a positive quantity which is lesser than C2, that is, since C1 is lesser than C2, this quantity would be less negative than this quantity. So my alpha dash double dash is the required, so alpha double dash is actually lying between alpha star and 0. So alpha double dash is actually my required alpha dash for which the Wolf condition is satisfied. So here we have a proof. Now we are going to discuss about how do I actually apply this sufficient decrease. So this sufficient decrease is done by a method called backtracking. So how do I choose my backtracking principle? So how do I choose my step length? By using backtracking principle. Now this is also called Armizo principle due to the mathematician Armizo. So this is quite often applied in algorithms, and to get a result quite fast. So you choose alpha bar, some alpha bar greater than 0, and choose a row between 0 and 1, and C between 0 and 1, that is a C1 actually. Now initialize alpha with alpha bar, some alpha bar you have chosen. Now repeat until you have f of xk plus alpha dk. So until, so dk is a descent direction. So how do you find this alpha bar? This is the following way. Let's see. So if you find an alpha, take an alpha, it's alpha bar, and you see that this condition is not met for a given, that for the chosen C, this condition is not met. What you do? So if this condition is not met, you reduce alpha by a certain amount. You take a fraction of alpha, and say if it is alpha bar in the starting, so you take a fraction of alpha bar and put it to the new alpha, and then check with the new alpha whether this condition is satisfied with this particular C. If it is not, and then go on, basically doing. Then when such an alpha is found, set alpha equal to alpha k and terminate. And then xk plus 1, the new point is xk plus alpha k dk. Okay. So, this is what is done in actual practice. Now, let me give you one or two examples. For example, how would you find, let me take an example from the exercise of Nose et al. So, let us try to summarize what we have learned in this section on descent directions and finding the control step length, by which you control the movement from xk. So, you take a function of two variables, and the function of two variables here is x1 plus x2 square whole square, and we are taking at x, the point x as 1 0, and they are giving us a direction d minus 1 1. Now, the question is this d a direction of descent from this point 1 0. So, how do I first know that whether I need to have a descent? To have a descent, I first have to find the gradient of this function. So, the gradient of this function okay. This function, if you look at it, I have to compute this value and this value at the points 1 0. So, what is my del f del x1 here? Del f del x1 is 2 times x1 plus x2 square, and into x1 is 1. So, by chain rule. So, del of del x2 is 2 times x1 plus x2 square into 2 x2. Now, if I put here, I compute the value at 1 0, that is I put x1 equal to 1 and x2 equal to 0, then what I get here is 2, and if I put x1 equal to 1 and x2 equal to 0, then what I get here is 0. So, this value at 1 0 is nothing but 2 0, and this is not equal to 0, and hence this point is not a point of local minimizer. So, this is not a critical point. So, then I have to move to a better point from 1 0. So, what I do to check that whether this is actually a gradient or not? To do this, I have to check this one. I have to see whether grad of fx into d, what is this value, which means I take the inner product del of del x1 into 1 plus into minus 1 plus del of del x2, both are obviously computed at the point 1 0 point 1 0 into 1. So, this computed at the point 1 0 is 2 into minus 1, this computed at the point 1 0 is 0, so 0 into 1. So, what I get is minus 2, which is strictly less than 0, showing that this is indeed a descent direction. Now, let me give you a homework from the book of Nose et al. And write, and I expect that you really go ahead and look into this homework. because that would give you little practice, because till the beginning we had not done any practice here. So this course is essentially a course at the advanced graduate level and advanced undergrad level and beginning graduate level. So we really need to pull up our socks and look into examples. So now I give you an example, a very important test function which is used in optimization to do the job, do various demonstrations of algorithms. So here this is called the Rosenbrock function. Let me again show you the reference of the book that I am using here. The book called Numerical Optimization, and it is written by Nosedal and Wright. It is published by Springer and it is now available in Indian edition. I have already mentioned it, but only minimizer of the problem. Can you show that, so hence can you show that it is the only minimizer of the problem? So I am giving a apostrophe here. So I am asking you also, is this a global or a local minimum? Tomorrow we will start discussing the steepest descent method, and after we discuss steepest descent method I will give you a solution of this problem. But I expect all of you to really have a look at this problem at home and try to do this problem. This is a very, very important function and has gives a lot of demonstrations when you study numerical algorithms. Now what I want to ask you is the following. Function f(x) equal to norm of x square. X is in R2. So f is a function from R2 to R, and my f of x1 x2 is equal to x1 square plus x2 square, which is norm x square. Now let me write down an iterative algorithm to minimize it. That is, I am writing down some sort of iteration, that is how I go from xk to xk plus 1, right. Now let me take kth iteration is of the form into cos k and sin k. What I am asking is to show that this also we can discuss tomorrow after we discuss steepest descent method. So this just show this. So these would be two problems for you which you have to show, that here you see the iterates, the function value is decreasing. Think about the geometry of this, but please keep a note that you have to do this. Thank you very much for today, and tomorrow we will get into this exciting thing of steepest descent method, and we will use steepest descent method for the particular class of quadratic optimization problem where the Hessian matrix is positive definite, and we will show how we can understand rates of convergence and other issues related to an optimization algorithm. The optimization algorithm in the unconstant sense is not just solving grad f(x) equal to 0, that equation, but it also has to entail that every xk plus 1, every k plus 1th iteration, my function value has to be better than f of xk. So that's the important thing that one has to realize one does when one uses an optimization algorithm. So thank you very much for today. See you tomorrow.